Okay, geometry 8.7 is really nothing new in terms of concept. We spent a lot of time talking about sine, cosine, and tangent, and SOHCAHTOA, and that kind of stuff leading up to this. And now they just want to throw a bunch of word problems at you that involve all that stuff. Now remember, trigonometry sort of ended here with SOHCAHTOA. It was the last thing we did before 8.7. But don't forget that there's some other things that are part of this chapter, and I'm going to be throwing at you in these word problems that are easy to forget when you get so buried in SOHCAHTOA. Like, you can save a lot of time if you know that the triangle has some 45 degrees in it or some 30 degree, 60 degree angles in it. Also, don't forget about Pythagorean Theorem. We're doing some trig right now in FST, and there's a lot of problems that buried somewhere in the middle, there's a step where you have to use Pythagorean Theorem, and people forget about it. That if you know two sides in a right triangle, you can easily find the third. Or if you have three triangles, you can find, three sides of a triangle, you can quickly figure out whether or not it is a right triangle by using the converse. That is, if a squared plus b squared equals c squared, then you can tell that the right triangle, that it is a right triangle. Geometric mean, not so much. I just listed it here because then that gives you one nice place here in the middle of this notes section to tell you about everything in this chapter, really. That's it. The only other thing I mentioned right here is that if there's a square root, you might have to simplify. Be sure to do that, otherwise I won't be extremely happy when I take off points for that, because you left something like 2 divided by the square root of 3. That's not really the correct spelling. Okay, so what kind of problems are you going to do? Well, there's a lot of problems where they talk about this thing called angle of elevation or angle of depression. Actually, let me go back to this for just a second. Angle of elevation, angle of depression. There's a thing on page 317 that shows you what that is. But when they talk about angle of elevation, angle of depression, they're talking about some real life problem where there's something up in the air or some high cliff or something like that, and somebody who's looking down from that, or someone here on the ground who's looking up at something. Things like angle of depression and angle of elevation are basically that angle between sort of the line of sight. So that, like, say you're in that airplane, you're looking down like this way, and sometimes you can draw a little eyeball. This little eyeball here, and say, okay, we're looking down that direction, and you're at some height, and you're looking at the ground. The angle of depression, it doesn't mean that this angle is psychologically challenged or something. It just means that that there's this angle that you have to turn your eye downward compared to what if you would be able to just look straight. So if you're looking straight, that would basically, you'd consider that angle depression of 0 because you're looking absolutely straight. And if you look downwards here, whatever degree this is the angle of depression. The converse of that, or so the other end of that, is what if you were standing down here, and you're asked to look at, the big giant eyeball in the sky. Okay, this picture doesn't make as much sense now because of the big eye there before. But, say you were here, you're trying to look at the top of a mountain, or look at the top of a cliff, or look at, the height of an airplane or something, which is what I'm going to do here in a second. If you were just looking straight, that would be angle of elevation of 0. But the amount you have to crane your neck and look upwards, that's referred to, that angle there. That angle against horizontal, it's a degree symbol, is called the angle of elevation. Well, if you call this one the elevation, I don't know if I can write this small on these things. Okay, if this is elevation and this is depression, and they're both compared to, horizontal directions, here you've got angle of, we're really talking about two external designs. Angle of depression kind of looks like that, angle of elevation kind of looks like that. And these are both horizontal. Really what we've got here are two equal angles anyway, so who cares whether or not you refer to that angle as the angle, measured up here from horizontal, or, it's measured down here from horizontal. It doesn't matter. It's the same angle. There is really no name for this angle in here. Like this angle right there, whatever that is, I'll put 2 little stripes here because it's different. That one doesn't have a name. Be careful about measuring that angle or referring to it, or if it's used in a problem where they talk about depression or elevation, because this really isn't anything. It doesn't have a name, I should say. It can be a useful angle, and maybe sometimes they give you that angle, but that's not the angle that gets a name. So just real briefly, my stance on depression and elevation there. Okay, so here's a problem with an airplane in it, and let's say we know the height of the airplane is at, I'm going to call it altitude because that's kind of how they usually refer to airplanes. Let's say the altitude is 35,000 feet, which is not an unusual altitude for an airplane. And let's say that it's, I don't know, 100 miles from where it's supposed to be landing. And it's looking down here, or it's thinking about making sort of a turn here, making a little bit of an angle change from horizontal and starting to go downhill, starting to descend, basically, to land perfectly at the airport. Okay, so the question is, find the angle, because they might say it this way in the book, and I don't want you to get all bent out of shape about it. Find the angle of depression, as if it's depressing to land an airplane. Okay, find the angle of depression going on here. Well, angle of depression technically isn't even drawn here. Angle of depression would be measuring that distance from, sorry, the angle from horizontal. Can I draw this here? Is that too much trouble? Yeah, angle of depression is this little tiny angle in here, which is kind of hard to see in this context. But yeah, there's a little tiny angle of depression right here. And you're looking at this picture and you're going, oh my gosh, these things are almost parallel. What am I going to do? Well, that angle of depression, what I just said in this other little argument, is that's the same as this down here. So really, we don't even have to worry about trying to draw that line so crazy. We can just go, you know what? I'm looking for this angle right here, because it's the same as that little angle of depression out there, if you believe in AIA, which you should by now. So I'll call this X. It looks like I drew an X there for the airport. So I'm looking for the measure of angle X. I know this side, and I know this side. Now this right triangle is kind of long and drawn out and pointy, and it's kind of hard to see where the hypotenuse is. But believe it or not, this blue thing is the hypotenuse. And in most of these line of sight problems, the hypotenuse is not a practical length to even talk about. Who really cares how long this sort of imaginary, diagonal thing is in this problem? I mean, the airplane has got a height, and that's something we can measure and we care about at any one time. The distance on the ground to the airport, yeah, that's a perfectly nice thing to talk about. But no one really talks about the length of some imaginary wire connecting the airport to the plane. There are some problems like that, but really it doesn't come up that often. What I'm going to care about more in these problems are things like this, the parts that meet at a right angle, which relative to angle X, this one, of course, you remember from last section, is the adjacent, and this is the opposite. Oh, by the way, this is in feet, this is in miles. That's another thing they do to annoy you, so get ready for that. Actually, since I just mentioned that, since we're talking about feet here and miles here, we need to make sure those are the same thing, same units. 100 miles is in feet. If there's 5,280 feet in a mile, I multiply that by 100 to get total feet in 100 miles, which is over 500,000 feet. Okay, so now I know opposite and adjacent in the same units. Opposite and adjacent, we're in a fraction like this, and that's the one we called tangent in TOA. So that means here I'm going to be talking about tangent of angle X is going to equal 35,000 divided by 528,000. Now that's a whole bunch of zeros in the same fraction. Let's reduce that to make life a little simpler. This is 50, sorry, I wrote it right, I said it wrong. 35 over 528. So if I want the measure of angle X, all I got to do is take the inverse tangent of that fraction. And let me do that on the calculator here. Inverse tangent of 35 over 528 is an angle of about, it's less than 4 degrees. And you would kind of expect, remember how pointy this thing looked? 3.8 degrees is pretty sharp angle. And it kind of looks like a sharp angle. I mean, this thing is really hairpin. Of course, I don't think I drew this triangle completely to scale either. I mean, if this is 35,000 feet, is that really like 100 miles? I don't know. Probably something like that, because that would be a pretty slight angle. Technically, by calling this angle of depression, we're actually looking at the angle comparing this blue segment to the horizontal here, which is really hard to draw, and it's really hard to compare that to a triangle. Just realized by AIA, yeah, we're talking about this down here. Okay, here's another type of problem you might get, which is looking for a side of a triangle when you know one angle and one other side. Just a word problem version of something we could have done last section. All right, angle of the sun in the sky is at an angle of elevation of, here, let's get a nice sunny color here, of 38 degrees. So pointing to the sun, and that's, kind of hard to see sometimes, but let's say the angle of the sunlight coming out of the sky is an angle of 38 degrees. Let me write that in there. Then, so that's given. Angle of elevation. So if you're standing here and you're looking up at the sun, your eye has to turn skyward by 38 degrees. That's what this means. The building's shadow, this is this segment on the ground in black here. The building's shadow is 45 meters long. The question is, how tall is the building? Okay. Well, relative to the 38, we really can't do Pythagorean Theorem yet. We can assume that the building's standing at a right angle. We can't do Pythagorean Theorem because we don't know two of the sides. We just know one. A squared plus b squared equals c squared is going to get us nowhere. But we have an angle and we have two sides that we care about. One we know and we don't. So remember in all those SOHCAHTOA things, each one of those involves an angle and two sides, and we've got two of those three ingredients here. So then the question is, which one do we want, sine or cosine or tangent? Here, relative to 38, once I call this 38, then this is what I'm dealing with here. This is opposite and this is adjacent. The one that deals with opposite and adjacent, just like the last example, because again, who cares about this length in the problem? It doesn't really have a name or make any sense, but building height and shadow length, yes. All right, so the one I care about is the one with opposite and adjacent, and that is the one that's going to come out of the calculator as tangent. So here we go. Tangent of 38 is opposite over adjacent, and we go from there and do some not so fancy algebra. All I gotta do is multiply both sides by 45 and I'll find b, and that is approximately, handy dandy calculator, 45 times the tangent of 38 is just about 35 point, should I say 2? 35.2, sure. 35.2. Yeah, and that looks pretty reasonable, actually. That this should be a little bit less than that because that angle is smaller than 45. You'd expect opposite over adjacent to be less than 1, or that this side should be slightly shorter than that side. Okay, I had to make up one more problem just because I wanted to get some things in there that might not have shown up otherwise. Okay, and I made this one up, you can tell, because it has to do with interim. All right, so let's say you were on one of those hiking adventure trips, and a lot of those trips, they talk about how much you walked vertically in a day, and that's kind of an interesting thing to know about because it can be really hard, and it would explain why your knees hurt and that kind of stuff. Let's say you have a pedometer that you are pretty sure is really accurate, and you know you were walking straight uphill all day, pretty much. You know that was 15 kilometers, and that was the distance you actually, touched with your feet. So that is this. That's why I want to include a problem like this, because it actually does use the diagonal measure, and we don't get that very often. But let's say you looked at point A and point B on the satellite picture from above, looking straight down, and you could see this distance from space, and you measure it, and you're sure that that's really accurate, and that's actually 14.8. And you go, well, maybe my pedometer is just a little bit off, but let's make sure that let's pretend that it is really accurate, and that you can believe this number and you can believe this number. Well, then the difference then is explained by the fact that you are also walking up, and the pedometer counted your steps going up, whereas the space satellite only, talks about your longitude latitude change, not your altitude change. So we need to find this thing over here. I'm going to call it A. Actually, well, here is for the first time in a long time we actually have two sides of a triangle. We need to know the third side, so I can use Pythagorean theorem to find that, and that would be a really interesting thing to know. And this is one of those where I don't know one of the legs, so you got to be careful here that you don't just say 15 squared plus 14.8 squared, but it's actually 14.8 squared plus a squared equals 15 squared. With the calculator, I do that pretty quickly, and I find out, I think I already did this on the calculator. Let me do this one. Yeah, if I take 15 squared minus 14.8 squared, I get that. And I square root that, and I find out that it's really close to 2.44. Actually, I'll just do this. I'll just go straight to it. I'll just say, yeah, we use some fancy algebra. Oops. That should actually be red. Watch. Ooh. Yeah, watch. Watch me change this color really fast. Change that to red, because this is the answer. Okay. And then I found out that A was really close to 2.44. Okay. Now, if I want to find that angle at A, sorry, big A down here, if I want to find this angle, what was your angle of elevation during the day? That's also good to know too. You might want to talk about, well, we were walking at this altitude. I trust my 15 and my 14.8 more than anything else, so I'm going to use the trig ratio that uses those two given numbers rather than, if I made a mistake here, it's going to affect that answer. So here we're dealing with the adjacent side and the hypotenuse side. Adjacent over hypotenuse is that fraction, and if it's adjacent hypotenuse, we're talking about cosine. So all I have to do is this. I'm going to do that on my calculator. And I see that that's about 9.37 degrees, which ain't half bad. Thank you for watching.